B5. So the decomposition of sulfuryl chloride is first order with a half-life of 245 minutes at 600 Kelvin. An evacuated flask is filled with SO2-Cl2 at a pressure of 9 bar at 600 Kelvin. Calculate the partial pressure of each gas after 6 hours have elapsed. Right? So, if we're thinking about it, right, 245 minutes, right? The first thing we can do is we can convert 6 hours into minutes, right? So this is going to be T is equal to, right? So 6 hours times 60 is 360 minutes. So right off the bat, right, one thing we should know is that we're going to go through at least one half-life, or we are going to go through a half-life, right? We're not going to complete a second one. In these cases, right, we're going to be at, I think, basically 1.5 half-lives roughly in those cases. And so now the question becomes, how do you figure out what the half-life equation is, right? So we know it's first order, right? And so what we can do is we can derive it, right? So we have the natural log of A, right? So this is the integrated rate law, is equal to the natural log of A initial minus KT in this case. And so now, the question becomes, how do we derive this right here, right? So if we have an initial concentration of 1, right, and then we end up with a concentration of 0.5, right, which is essentially half of what you have in that case, right, the question becomes then, right, and we know that T in this case, right, is going to have to be 245 minutes in that case, right? The next question becomes, what the relationship is, right, with K and so forth, right? So if we take the natural log of A minus, all right, natural log, let me just do the math. Natural log of 0.5 is negative 0.6931 is equal to the natural log of 1 is equal to 0, which makes sense, minus KT. Right? And so then in that case, what we can do is figure out that T is going to be equal to 0.6931 divided by K in that scenario, right? And so knowing that right there, right, we can rearrange this. So we can figure out K, because that's actually what I'm trying to get to. So right, K is equal to 0.6931 over time. In this case, right? And so then in this case, right, time is, the half-life is 245 minutes. So that becomes 245 minutes. So K in this case is 0.6931 divided by 245, which is then 0.00289. Right, so we have the K value there. So now we can just simply plug that in up into our like actual equation, right? Because our initial pressure is different, right? And we can just use it doesn't necessarily have to be concentration, right? Because we can go through, and if you remember back from the thermal part, right, since the volume isn't changing, right, the pressure is going to be directly related, and the temperature isn't changing, right, the pressure is going to be directly related to the number of moles. And so, right, they just go hand in hand, excuse me, in that scenario. So what we can do is the natural log of 9 bar is equal to, or not equal to, minus k, which is this value, which is 0.002829 times the time, right? So it's going to be 360 minutes, right? And then this is per minute. It's going to be equal to the natural log of SO2 CL2, right, at 360 minutes. And so the natural log of SO2 CL2 at 360 minutes is going to be equal to natural log 9 minus 0.002829 times 360 is 1.178. And so then if we take everything to the e to the power of that, what we get is that the concentration is, after 360 minutes, is equal to 3.25 bar in this case, right? So we're at 3.25 bar, right? So that's how much is left over. And so now in terms of thinking about the pressures of SO2 and CL2, right? Because, you know, it's a 1-to-1 relationship, right? For every mole of SO2 CL2 that is, you know, decomposes, you end up with 1 mole of SO2 gas and 1 mole of CL2 gas. So then for the concentration of, or this should be pressure, I guess you could say, right? And then for the pressure of SO2, right, which is going to be equal to the pressure of CL2, that's just simply going to be equal to, right, the initial pressure of SO2 CL2 minus the pressure of SO2 CL2 final, right, in this case, which is 9 minus 3.25, which comes out to being 5.75. Right, and so that's how you approach that right there. So you don't have to worry anything about, you know, equilibrium or anything like that, right? Because the equilibrium probably is very much in favor of the decomposition from happening. But you don't, right, for this type of problem, you don't have to worry about that right there.